Hi guys, this is some notes on triple integrals, and now we're going to convert these into cylindrical and spherical coordinates eventually. We're going to start with cylindrical coordinates, and what we're doing is basically changing something from polar coordinates and R2 to R3 being cylindrical coordinates. So here we are down here in polar coordinates like we've seen before. We're rotating off of that positive x-axis like we've been doing in polar coordinates, some radius r. But instead of just stopping at that point and calling it r theta, we are going to go up from that point. That's the input, and then the output is this value z, and z basically takes in r and theta as an ordered pair rather than x and y, and it outputs a height z. Very similar to the idea of polar coordinates combined with the idea of three-dimensional function. So the same thing is happening here that happened with polar coordinates, except for just that one extra piece that now we have a height above where we end up when we make that rotation. Alright, so this is asking us sketch these following sets in cylindrical coordinates using this concept of rotating around from the positive x-axis and then adding some type of function onto it. So Q, the set Q is all of these r, theta, z, these ordered triples, such that r is between 1 and 3 and z is positive, or non-negative at least. R is between 1 and 3, so if you can imagine r between being 1 and 3, that's not going to include r being 0 all the way up to 1. So we're going to have, like, there's a 1 and there's a 3. Alright, so up here there's a 1 and there's a 3. And so we're going to rotate around to those. We're going to go all the way around. This is just the first quadrant. So we're going all the way around. And then we have z is greater than or equal to 0, so that's going to go up like that. Okay, because 0 is included, we would have solid lines on the bottom, solid lines all the way up wherever we cut this off, which we don't. It just keeps on going up in theory. Okay, but we would have a hole here in the middle where it's not part of our domain down here in the xy plane. Alright, so there's what A would look like. And then B, if you read B, it says z equals 1 minus r. Right, and r is between 0 and 1. So just like before, it's not telling us theta, so we're just assume theta runs the gauntlet from 0 to 2 pi. And again, there's x and y, and r is going to go from 0 all the way up to 1. So let's say there's 1, there's 1. So we're going from there to there, and we're rotating around, and again, we're going to go all the way around. But now z, the height, is 1 minus r. So when r is 1, the height is 0. 1 minus 1 is 0. When r is 0, the height is 1 up here. Alright, and as we make our way this way, the height comes down. Alright, as we make our way this way, the height comes down. So you can see this is going to be a cone in 3 dimensions. Right? When we plot all those cylindrical points there. And there's just a little bit better of a picture of it drawn with computer software. But you can think through what these things will look like, just giving a rough sketch like I did on the last slide. Alright, now the transformation between rectangular and cylindrical, well, as you might imagine, because we got that polar domain going on, we still see the same things. R squared equals x squared, tangent theta, x equals r cosine theta, y equals r sine theta, and then this z equals z concept. It's just the height is the height. Okay, we're just instead of having an xy pair being down here in the domain, and then that input gets mapped to a z based on the function. Well, now we just have, instead of xy, now we're calling it r and then theta, which is required to rotate to get me around there to that point. So it's why we're seeing z equals z. Now we're going to get some a little bit different stuff later on, but it's really all we're doing is just adjusting these first two pieces right here to be basically from polar to rectangular, rectangular to polar. That's really the only difference here. Alright, so the first part says find the cylindrical coordinates if these are the rectangular coordinates, 1, 1, 5. Well, I can do this part for you. Alright, 5. And then 1, negative 1, that means, x, y. So we're going to use this to get r. So r equals, I'm just going to call it r equals the square root of this plus this squared. So 1 plus 1. So r equals the square root of 2. So that's r. And then theta, we can get theta from arctangent y over x. So that would be negative 1 over 1, which is negative 1. And the arctangent is negative 1. Our tangent's negative 1. Arctangent's going to tell us that it's negative 45 degrees or negative pi over 4. Okay, but typically they'll ask you for a positive angle there. So, or you can also say that that's positive 7 pi over 4. Either way, just add 2 pi. Now, I would not have any problem if you would have used negative pi over 4 in that position. It's perfectly fine. Alright, and then the second part wants us to go the other way to find the rectangular coordinates. If these are the cylindrical coordinates. So r equals 2, x equals r cosine theta, so that's 2, which is a half. So 2 times a half is 1. And then y equals 2 times the sine of pi over 3. So that'll be the square root of 3. So we've got x, y, and then z is still the same z. Really the only difference between this and polar coordinates is there's this third coordinate in both cases. Alright, and that's what's making it a cylindrical coordinate. Alright, now when we integrate with cylindrical coordinates, I'm going to show you where this formula is coming from briefly. Think about if we had this cone from the earlier problem and we are going to integrate with respect to not the rectangles going straight up from the base up here, but if we are again doing it with polar, we're rotating around this way. So we're creating these wedges, these sectors, and then if r changes, it's going out from the origin out. So we're talking about a wedge like this to that, and then we're going up until we hit the curve. Alright, something like that. And these are the things that they're going to look like this. These are the things that we're integrating, and we have several of these at different places on here, and they are all being approximated and added up like a Riemann sum. But I want you to take a look at what we are coming up with here. So what we're saying that these things are, if you look down here at the bottom, this is arced and this is arced, right? It's not a perfect rectangular base, okay? We are going to approximate it as if it were, okay? And the rectangle we're creating, we're saying that if we went to the center of this thing, so the center of this thing is, we're using this r with a bar on top of a notation, and the middle of this angle we're calling this. So it's like the midpoint of the rotation from the first dash part to the second. So right there, halfway in the middle, is that theta with the bar on top of it, right? And then the same thing, the r with the little dash is right there in the middle as well. So we're saying, yeah, this one up here is longer and this one up here is shorter, but if we stop right here in the middle, that piece right there, if we created a rectangle with this piece right here as one length and delta r as the other length, then we would approximately Again, this is arced, but because this one's longer and this one's shorter, if we use the mid area, we would have a length that's basically the average of the two, and we could approximate that with a rectangle. If we use this on the lower end and on the upper end. Okay, that's kind of the thinking. Then we're just going to straighten this out on both ends and make a rectangle. Now, what would be this length? Well, it's arc length, and the arc length formula, S, we use S for arc length, is equal to r theta, where r is the radius and theta is the angle that's swept out. So it's a approximation, but as these things get smaller, and they're going to get smaller as n goes to infinity, it becomes a pretty good approximation, and actually becomes exact when these things get infinitesimally small. So because this is the approximation, there's that r with the bar over it, the mid radius of that thing, and that arc length that we cut out right there is r bar times delta theta. Okay, and then this length up this way is delta r. So what we're saying is this area of the base down here is approximately r delta theta. Okay, so once again, just like we saw back in polar coordinates when we're integrating polar coordinates, we're going to end up with r dr d theta, but now dz. Okay, so it's just going one step further because of the z height, but the r dr d theta is going to be there with cylindrical, and then we'll also see it's there in polar, but we're also going to have another piece multiplied in as well on top of it. Okay, so just once again, because of the polar nature of the domain, we're seeing the r dr d theta again. Alright, now notice here that they do set up in this definition, they put r in amongst after the first differential. Okay, but that's perfectly fine to go ahead and multiply that r through in the function itself, rather than waiting to the r step for whatever reason. Even though technically you could, since r would be a constant when we're integrating over z, but it's also fine to go ahead and put that r in there. And notice here too that if the original functions you are given to you in terms of x, y, they're rectangular type functions, or not necessarily even functions, if they're just rectangular relations given with x and y as your independent variables. Notice if we're going to change it to cylindrical coordinates, we do need to change the x and y's that are the independent variables in the original integrand need to be changed there, and they also therefore need to be changed in your limits integration when you do any substitutions. Alright, so we are integrating this integrand. Again, we see the radicals. This would be a good time to use cylindrical coordinates. Okay, so when z itself is a constant function like this, and then you have x and y have that radical nature to them, and the integrand itself has that radical nature to it, that's a good candidate for cylindrical coordinates. So this right here, notice underneath there we got a r squared, so I'm going to rewrite the integrand as 1 plus r squared underneath that radical. Alright, z is still going from -1 to 2. Alright, and then this dy dx, if you notice, these are down here, these are, because this is the second one, these are y's, so y equals, so if I square both sides, I'll have a y squared equals 8 minus x squared, which adding the 8 over, I get x squared plus y squared equals 8, which means this is a circle in polar coordinates, and the radius is the square root of 8. Or I could write that as 2 root 2. So r equals 2 root 2. that is the equation of that as a polar function. So that is our upper value for r, and then theta, of course, will go from 0 to 2 pi when we did polar. Okay, so there's going to be our setup, right? And then this is dz, and then r dr d theta. I'm just going to put dr d theta and stick in the r right there. Okay, and then that's coming first, so I could just integrate that, put those in. Anyway, again, the setup is the new thing that I'm looking for, that you can switch to cylindrical coordinates. If you made it to this point, I'm confident that you can integrate that by hand if needed to, with enough amount of time. But again, the setup is what I'm looking for here if you can switch it. Alright, same thing. Let me move this picture out of the way. The volume between two surfaces. So it's the same concept as before when we do these. We did a problem just like this in the last section, but we didn't use cylindrical coordinates. So before we would put 1, then like d, z, dy, dx, or however you wanted to set it up, dz, dx, dy. And then we would put this function up here and this function down there. But what we're doing here is we're trying to switch these things to cylindrical coordinates to be able to do this. So the upper and lower limit are not going to be the same, and then the limits of integration, the differentials here are going to be a little bit different. So this equation down here, z equals the square root of x squared plus y squared, where that's r squared, so the square root of r squared would be z equals r. And think about that for a second. If that's your radius, then that's your height on that level, and then the radius got bigger, so the height got bigger. Okay, so that cone down there, z equals r, that is the equation of that in cylindrical coordinates. Alright, and then up here, this is simply z equals 12 minus, that's r squared. So there's our dz. It's changing from, on the bottom, just r, and on the top, 12 minus r squared. Alright, and then the same thing. Where are these two things equal? That'll be this circle projected down into the xy plane. We can find its equation and make the last two be polar version of that circle in the xy plane. And we just have to remember again the dz, dr, dz, r, dr, d theta. Alright, neat little trick here. This, if I take all of this to the other side, I'll have x squared plus y squared plus the square root of x squared plus y squared minus 12 equals 0. Alright, now you may be looking at that thinking, well, what are you going to do with that? Or why didn't you just square both sides? This is the square root of this, right? So likewise, the x squared plus y squared is this squared. So this is what we call quadratic in form. If I let u equal the square root of x squared plus y squared, then u squared is equal to x squared plus y squared. Right? And I end up with u squared plus u minus 12 equals 0. And so I can factor that. That's u. So I get u equals negative 4, or u equals 3. Well, if u equals negative 4, that's the positive square root of x squared plus y squared equals negative 4. It doesn't make any sense. But if I have u equals 3, that's the square root of x squared plus y squared equals 3, which means, of course, that x squared plus y squared equals 9. So that's a circle, radius 3, right there. And so what would that be in polar coordinates? That would be just r equals 3, and theta is going from 0 to 2 pi again. Alright, so there would be your setup. 0 to 3, and then 0 to pi, and dz dr d theta. Alright, and then you could put all that into wolf once you get it all set up. Okay, so that's that's a little trick. If you didn't see to do that, if you squared both sides, you could eventually get there. Alright, that'll do this for this video. That is cylindrical coordinates, and we'll get into spherical coordinates in the next video.